Welcome. In this chapter, we are going to have an introduction to IP Multicast Basics. This is particularly IPv4 multicasts, but it really works almost the same way for IPv6. There are various services on a network. Generally, services can be classified into a number of types. First is what we call the point-to-point services. One sender sending traffic to one receiver. The other type is point-to-multipoint services, like IPTV. We have some kind of source, but this source intends to send exactly the same kind of traffic to several receivers, a certain group of receivers. Talking about services such as file transfer protocol and web services, the key characteristic of point-to-point services is that different users have different requirements for them. For example, a user A needs to download document A, but user B needs to download document B. In that type of service, we usually carry unicast mode communication, and the server sends different point-to-point data flows to different users. For point-to-multipoint services such as IPTV and video conferencing services, the key characteristic is that users have the same requirements for a particular service. For instance, users A, B, C, and D all need to watch video X. In that case, point-to-multipoint services can be carried in unicast, in multicast, or in broadcast mode. Now, if we decide to use unicast, or if we decide to use broadcast, there are known problems that we may encounter. So multicast is the one that has been found and has proven itself able to solve those problems. This chapter describes the advantages of using multicast to carry point-to-multipoint services like IPTV and video conferencing services, basic concepts of multicast, and the basic multicast forwarding process. Upon completion of this chapter, you should be able to describe and define the address structure of multicasts, that is for multicast IP addresses and also multicast MAC addresses. You'll also be able to describe the multicast data forwarding implementation. How exactly does data move from the multicast source all the way to the multicast group members? Because in multicasts, we are not sending to a particular member, we are not sending to a particular destination, but we are sending to a group identified by the multicast IP address. So a source such as 10.1.1.1 is sending traffic to a group identified by a multicast MAC address in the range of 224 to the address 239, as we are going to see. Now, in this scenario, the group members need to have subscribed to a particular channel or to a particular group in order to receive such traffic. We are going to be discussing the forwarding implementation of such data forwarding. We'll also be able to describe the reverse path forwarding implementation. Why is it necessary? How exactly is it done? And what is its importance? I'm going to break down this chapter into two subsections. First is the basic concepts of multicasts, and after understanding the basic concepts of multicasts, we shall talk about the multicast data forwarding implementation. This is where we shall talk about the concepts of reverse path forwarding and also multicast distribution tree. Let us start by analyzing the problems of using unicast forwarding or broadcast forwarding when we want to carry point-to-multipoint services. As we've mentioned, point-to-multipoint services can be carried in unicast, multicast, or even broadcast mode. There are various implementation modes on the live network. However, we say that some inherent problems, known problems, will occur in case you decide to use unicast forwarding or broadcast forwarding for point-to-multipoint services. The problems that might occur if you decide to use unicast forwarding are illustrated in this first illustration. And if you decide to use broadcast forwarding, we have the second illustration to show the problems. If we decide to use unicast forwarding, in this case, we are taking an example of a video source that intends to forward exactly the same video to multiple IPTV clients that have subscribed to that channel. Now, what is going to happen if we use unicast? If we use unicast, it means a particular video leaves the source headed to a particular IPTV client. So we need to send the number of videos equal to the number of clients we have. In this illustration, we have 4 clients, 1, 2, 3, 4, meaning that we have to send 4 different video streams to be received by those 4 clients, because each video has a unicast source and a unicast destination. It cannot be consumed by 2 IPTV clients at the same time. Now, what's the problem of this? Around the link from the source to the first hop router, there are going to be 4 duplicate packets. They carry exactly the same thing. And from the first hop router to the unicast network, there are going to be 4 duplicate packets carrying exactly the same thing. Now, because we have 2 IPTV clients on this side, we are going to have 2 duplicate packets carrying the same thing on that link, and 2 duplicate packets carrying exactly the same thing on that link, which is wastage of bandwidth. Now, although the traffic will come again with 2 different packets on that link and will get separated at the last point of division, we have wasted a lot of bandwidth. That is the problem. So what we're trying to say is that we have a large number of unicast flows that consume a large amount of bandwidth. And when there are a large number of clients, a large number of unicast flows are going to be generated. And one unicast flow is formed between each client and each video source. Because one unicast flow is formed between each client and each video source, we are going to have a large number of unicast flows in the network, and that large number of unicast flows is going to waste our bandwidth. That is if we decide to use unicast mode. From the source to the destination, 1 packet per 1 recipient. Now, of course, in the network, we have some ordinary terminals that are not subscribing to IPTV. They are not receiving, so that is a plus for unicast mode. Let us try to talk about broadcast mode. What is going to happen? Well, we know that in broadcast communication, one sender sends traffic and everyone on the network has to receive it. Well, that already gives us one of the problems. The problem is that an ordinary terminal that does not subscribe to IPTV and does not need to watch the contents of that video is also going to receive that frame. We do not want that to happen, and that can be a security risk. So these are the most common and well-known problems of using either unicast mode or broadcast mode for transmitting point-to-multipoint services. This is exactly where multicast comes in. If we decide to use multicast to carry point-to-multipoint services, a data flow is transmitted to a group of users along a multicast distribution tree, an MDT. Each link transmits only 1 copy of multicast data flows. So what is going to happen is that because the source is sending exactly the same traffic, it will send only 1 copy at this link. This copy will reach this point and it will get divided. A copy will be sent to that part and 1 copy will be sent to it. So every link will carry just 1 copy at a time. This 1 copy will be copied to another side of the link at the last point of division. That's when this guy will get a copy and that guy will get a copy. At the last part of division, that guy will get a copy, that guy will. But for every link, there will be exactly 1 copy of the traffic that is going to be sent on the link. That preserves a lot of our bandwidth. The replication is going to happen at specific interfaces where we have the 2 different interfaces or 3 interfaces combining into 1 link or dividing from 1 link to different recipients. For example, at this point, we are going to replicate the traffic, so we shall have a copy that side and a copy that side. At this point, we have 1 copy, and somewhere around here, we are going to have a copy this side. Of course, we understand there will actually be a switch somewhere around here to have the different recipients receive the different traffic if it is on the same network, but chances are this is actually on a very large network that probably covers the entire globe. So there are 2 main advantages associated with this. One advantage to solve the problem of using unicast, and another advantage to solve the problem of using broadcast. First of all, compared with unicast, multicast prevents the increase in the number of users from increasing the pressure on the video source or significantly increasing the consumption of network resources. In other words, if we get another subscriber, and another subscriber, and another subscriber and etc., all these will still consume 1 copy at this link. one copy at this link and one copy at this. The division will only come at the point of division closest to the subscribers. Secondly, compared with broadcast, multicast improves the transmission security because non-subscribers, ordinary terminals, will not receive the multicast flows. That is an important concept. One other thing, we have talked about the multicast distribution tree. This is simply the forwarding path of a multicast traffic or of multicast traffic. So how is this possible that traffic in one copy can leave the source and it will go on being replicated at every point where there is going to be division? Let us try to talk about the multicast data packet structure. The data packet structure of multicast traffic is really similar to that of Unicast. However, the destination MAC address and the destination IP address of multicast data packets are different from those of Unicast. Because in a Unicast data packet, the destination IP is going to be a Class A address or a Class B address or a Class C address, typical addresses used for Unicast transmission. For multicast, the destination IP address is going to be a Class D address in the range of 224.0.0.0 to 239.255.255.255. These are special addresses dedicated to multicasts. Well, although these addresses are further divided into certain groupings by IANA, but the groupings are multicast groupings. Secondly, the destination MAC address of multicast packets is a multicast MAC address. And we understand that interfaces of devices cannot be assigned multicast MAC addresses. So how do we get this multicast MAC address? We get the multicast MAC address by mapping it directly from the multicast IP address. We are going to talk about that in a moment. So the multicast destination MAC address is a multicast MAC address that is in the Ethernet frame header. The multicast source MAC address is a unicast MAC address, which is the source of whoever the multicast source is. The multicast source IP address is a unicast IP address, but the destination IP address is a multicast IP address in the range of the multicast addresses or Class D addresses. Let us talk about the IP address first, and then we talk about the MAC address. We have said the IP address will be something in this range, but can it really be anything in that range? Let us get into this a little bit more. For an IPv4 address space, Class D addresses, the 224.0.0.0/4, are used for multicasts. So a multicast IP address represents a point-to-multipoint data flow. For example, IPTV flow or video conference data flow. In most cases, different services such as IPTV and video conference services on the same multicast network need to use different multicast IP addresses. IANA further defines Class D addresses by grouping them into the following groupings. The first grouping is 224.0.0.0 up to 224.0.0.255. This is a total of 256 addresses. These ones are for permanent group addresses reserved for routing protocols. So if you know the RIP address, if you know the OSPF address and other protocols that use multicasts, if you know them, their addresses are ranging in this range. They fall in this range. The other range is the 224.0.1.0 up to 231.255.255.255. And then we skip to 233.0.0.0 up to 238.255.255.255. Now, you realize that we have skipped the 232 here. It's not there. But all these addresses are temporary any source multicast group addresses, ASM, any source multicast. We are going to come to that in a moment. The 232.0.0.0 up to 232.255.255.255, they are temporary source-specific multicast group addresses valid on the entire network. This is source-specific multicasts. As I said, we shall, by the end of multicasts, understand the difference between these two. The 239.0.0.0 up to 239.255.255.255 is temporary any source multicast group addresses valid only in the local administration domain. Realize that this is valid in the local administration domain and this is valid in the entire network. Now, after discussing a little bit about the IP address, we know that in the TCP IP protocol stack encapsulation, we shall need to encapsulate a layer 3, but then we also need to encapsulate a layer 2. How do we do this dealing with multicasts? How are we going to get the destination MAC address of a multicast? We know that the source MAC address is the MAC address of the multicast source. It is an interface. It can have a unicast address, but the destination is a group. It is not a single device, and yet we know that a MAC address is a physical address. How the hell are we going to get a physical address of a group? And how even are we going to find that physical address of a group? Let us talk about multicast MAC addresses. When a unicast IPv4 packet is transmitted on an Ethernet network, MAC addresses of receivers are used as destination MAC addresses. But when a multicast packet is transmitted, the system is different because the destination is a group of unspecific members, because any member can join the group at any time and leave the group at any time. You know, you can subscribe to my YouTube channel when you feel like, and you can unsubscribe when you feel like. How does the communication happen? How is this implemented? You can join a video conference at anytime you feel like, and you can leave it. How do you start receiving the streams when you join? How do you get attached to the MAC address so that you receive the communication? And how do you get detached from the MAC address when you leave the group? Now, as defined by IANA, the most significant 24 bits of an IPv4 multicast MAC address are always these. So, the first first 24 bits are 0, 1, 0, 0, and 5E. The 25th bit is a 0. This is how they are. And then the least significant 23 bits, this is the important part, are the least significant 23 bits of the IPv4 multicast address. Let us look at an example to better understand this. If we have an IPv4 multicast address of 224.0.0.11, that IPv4 multicast address is going to be mapped to the multicast MAC address of 0100.5E. These ones always remain constant. The 5th bit here is going to be a 0. The rest of the bits are going to be extracted from the IP address. Let us get this right. This is an example of a multicast MAC address. Has 48 bits. And we are saying the first 24, 8, 8, 8, are exactly these converted to binary. We are saying the 25th, this one right here, is 0. This has been defined by IANA. And then we go ahead and say the last 23, see, we have 24 corresponding to that, and then the 1 is 0, 25. What are we left with to get 48? 48 minus 25, we are left with 23. Now we are saying these 23 are mapped from the multicast IP address. Direct mapping. And then we have a complete multicast MAC address. That is very, very important. But it has an interesting thing to it that I want to note right here. We are saying the most significant 4 bits of an IPv4 multicast address are always fixed. These 4 bits are always 1110, which map the leftmost 25 bits of the multicast MAC address. These 1110 map the leftmost 25 bits of a MAC address. Among the last 28 of the IP address, these 28 from here moving there, from those 28, we use 23, listen carefully, we use 23 to map to the multicast MAC address. What does this mean? The 4 are constant, and the 23 are used to map to the MAC address. That gives us 27 out of an IP address of 32 bits. What are we trying to say? What am I trying to say? There are 5 bits that are lost in the conversion. For example, if you actually have the IP address 224.0.1.1, also 224.128.1.1, this is after taking the next bit, converting it to 1, and also 225.0.1.1, further conversion, 239.128.1.1. All these addresses, interestingly, all these addresses map to 01, 00, 5E, 00, 01, 01. So they will all have the same MAC address, and this must always be taken into consideration during address assignment. Now, IETF, Internet Engineering Task Force, knows that, but they believe that this is not going to cause a serious problem. Why? There is a very little probability, extremely little probability, that 2 or more group addresses, 2 of these or more of them, can be mapped to the same MAC address. They can't be in the same local area network. Imagine you can't have this in the same local area network with this. They are too far apart. You'll be having too many groups, which is not normal. So a multicast MAC address identifies a group of devices, and the least significant bit of the first byte in a multicast MAC address is 1. We have seen this from our HCIA material, that in a multicast MAC address, the least significant bit of the most significant block is 1. And the devices identified by the same multicast MAC address are in the same multicast group. Those devices listen to data frames whose destination MAC address is the identified multicast MAC address. And the destination MAC address, if the destination MAC address is the multicast MAC address, it means whoever listens to that MAC address will receive the frames destined to that destination. As an example, BPDU payload of STP protocol is normally directly encapsulated in Ethernet data frames with no IP header. With the destination MAC address, normally, actually not normally, for BPDUs, it's 0180 C200 0000. Well, you should actually be knowing this, which is a multicast MAC address. How do we know this 01? The least significant bit of the first octet is a 1. There are many similar examples that have something like this, but we don't list them here. They are not important for this class. And these multicast MAC addresses are not associated with any multicast IP address. And also, we need to pay special attention to the multicast MAC addresses that map multicast IP addresses, because the multicast MAC addresses described in this entire chapter are those ones that map to multicast IP addresses. Now that we understand where an IP address for multicast traffic comes from and where the MAC address of multicast traffic comes from, let us try to understand the basic architecture of a multicast network. Now, a typical multicast network actually has a total of 3 sections. We have the source end network, we have the multicast forwarding network, and we have the receiver end network. The first section is the source end network, the second section is the multicast forwarding network, and the third section is the receiver end network. These are the 3 parts of the multicast network. The source end network is the one that sends the multicast data that is generated by the multicast source, and it intends to send this multicast network into the multicast forwarding network. The multicast forwarding network is in charge of generating a loop-free multicast forwarding path, which is also referred to as the multicast distribution tree. It's supposed to be generated by the multicast forwarding network. That is where the multicast routing protocol is going to be deployed. The receiver end network enables multicast forwarding network to detect the locations of the different members that join different multicast groups. There are different protocols that run in each of these sections. Now, for the first section, source and network, there is really no serious protocol necessary. All we need is connectivity between the multicast source and the first hop router. That router is called the first hop router, and this router is called the last hop router. Of the multicast router, they are both multicast routers. First hop router, last hop router. Now, in between these sections where we have the multicast forwarding network, we have a number of protocols that run here. But for this purpose, I'll mention PIM. We shall have an entire chapter on PIM, SM, and DM. The multicast forwarding paths are established based on multicast routing protocols. And on the receiver end network, we need some kind of protocol to help this router know which members have joined which group and which members have left which group. Does this group still have members interested in receiving its packets? Something like that, and IGMP is our candidate here. We're going to talk about IGMP also. We have an entire chapter for IGMP. Having this kind of network gives us particular service models for multicast forwarding. Because when receiving multicast data, multicast group members can select the multicast data sources. That's option 1. There are 2 multicast service models available. What we call any source multicast and source-specific multicast. And this is really easy. It's the terminologies that make it sound difficult. Any source multicast and source-specific multicast. Let us use these 2 figures to explain what these 2 mean. If we have a multicast group member which simply says, hey, me, I want to receive traffic from group 2. Traffic headed to group 2, send me a copy of it. That's all he's saying. He doesn't care who is the source of this traffic that is going to group 2. Because John can send traffic to group 2 and Alex can send traffic to group 2. But if this particular group member is saying, no, just send me group 2 traffic, I don't care who is sending. This is called any source multicast. I don't care who is the source. From any source, if it is group 2, just send it to me. Now, some group members can specify a specific source. It says, I want to receive traffic that is destined to group 2 as long as it is sent by Alex. This is very important because it's specifying a group and a source. So we shall have a specific source and group entry. For this case, we shall have an any source and group entry. As long as you're headed to this group, this member wants to get a copy of you. For this kind of entry, if you're headed to this group and it is this source that sent you, then this member wants a copy of that traffic. Those are the 2 models available. So after a member joins a multicast group, the member can receive data sent by any source to that group. That is what we call the any source model or the any source multicast model. The source-specific multicast model is when a member can only receive data sent by a specific source to the group in question. Those are the general basic concepts of multicasts. Let us now talk about the multicast data forwarding implementation. How exactly is multicast data forwarded from the multicast source to the group members that have subscribed to the destination network or destination IP? First, being multicasts, there are typical problems that might occur that accompany multicast data forwarding because it depends on routing entries. But if we forward multicast traffic based on routing entries, we are going to have a number of problems. The first problem is forwarding loops and duplicate packets. The second problem is suboptimal paths and duplicate packets. So either way you have duplicate packets, but then they can come with forwarding loops. They can even come with suboptimal paths. Let us look at this example. We have a multicast source right here that sends a multicast packet to the first hop router. The first hop router has a multicast forwarding entry based on the routing table. So the first hop router in its forwarding entry says, are you destined to group 1? Yes. Okay, you can be sent out of interface 1 and interface 2. So it sends the traffic out of interface 1 and out of interface 2. When this traffic gets out of interface 1 and interface 2, this router here, router 3, goes to router 3 here and router 2 here. Router 3 has its own, goes to router 2 here and router 3 here. Router 2 has its own forwarding entries. Says if you're destined to group 1, I will send you out of interface 1 and interface 2. This one also has its own. So what is going to happen is that when this router receives the traffic, it's going to send it out to interface 1 and again to interface 2. The same is going to apply for all these devices, thereby causing a loop and duplicate packets. The same packet this guy sent here, this guy will send back there. The same packet this guy sent here, this guy will send. Whereas it will also move it on, it will be duplicated over the network. BAM traffic. So the multicast group member will join group 1, and so the multicast packets will continue being forwarded for this member to receive. But if we forward only based on routing entries, this is the kind of problem we are going to have. We are going to have duplicate packets. We are also going to have forwarding loops. Also, considering the second topology here, having the multicast source that sends a multicast packet to the first hop router, router 1, that has a forwarding entry that says it should forward that out of interface 1 and interface 2. So it will send it out there and send it out there. Now the one that went to router 2 that specifies it can forward it out of interface 1 and interface 2 will go there. We are ignoring the one that goes here, but you can see there is still going to be a loop. But let us hold on with the loop problem. Let us send it here. This guy also has its own forwarding table, and he said it should send it out of interface 1, interface 2, and interface 3. So it will send it out there and also back there and back there. Now the important thing I want to bring to our attention here, that this is going to lead to a suboptimal path being followed instead of a more direct path. There are chances that this path will be followed instead of this path. How can we make sure that that does not happen? We need to use what we call multicast routing and the reverse path forwarding check. What is this and why is it necessary? Well, the answer to the second question is simple. It's just what we have just seen. Loops and suboptimal routes and duplicate packets may occur during multicast forwarding. To prevent these problems, in addition to the destination network and outbound interface, we need to define the inbound interface. You realize that when routing, we are only interested in where am I going, what's my outbound interface, which of course helps me know the next stop. But if we use this for multicasts, we are going to have these problems we have just mentioned here. The problems are loops, suboptimal paths, and duplicate packets. And now we are saying in order to solve those problems, we need to add some more information to these two pieces of information that we normally use for normal IP routing. For normal IP routing, the destination network and outbound interface can do us a great job. For multicast routing, we need to know the multicast source and the inbound interface information also. We need to add that information to the multicast routing entries. Then a device forwards only the multicast data received from a specific inbound interface. Now, this goes a long way in preventing problems such as loops, suboptimal routes, and also duplicate packets. But this one is only partially solved when we are doing multicast forwarding. For the same multicast source, the device can determine the unique inbound interface of the multicast traffic through what we call the RPF check, or the reverse path forwarding check. The reverse path forwarding check is based on the multicast routing entries. The reverse path forwarding check, as I've mentioned, prevents loops and suboptimal paths and also duplicate packets. Let us look at this topology for a moment. We have multicast source S1, and we have the last hop router that has a multicast routing table. However, this multicast routing table has extra pieces of information. As we've mentioned, it doesn't have just the outbound interface and the group, but it has the multicast source address, and it also has the inbound interface. Why are these extra pieces of information useful? So when router 1 receives the multicast packet from the multicast source S1, it will send the multicast packet out to router 2 and out to router 3. Router 3 and router 2 all have a multicast routing table. Router 2 will do a reverse path forwarding. It will run an algorithm to check whether this indeed is the interface that should be bringing in traffic from multicast source S1. Router 3 will do exactly the same thing. Well, for this case, router 2's reverse forwarding check will pass because this is indeed the interface closest to that, and router 3's reverse path forwarding check will also pass because this is the interface closest to that guy. Now, this reverse path forwarding check is based on the routing table, the IGP routing table. Now, what then happens is that router 2 will send the packet to router 3 through this interface. When router 3 receives the packet here, it will run the reverse path forwarding check. And when it checks this, it will see that this is actually not the closest interface to the source, and so it will discard that packet. This is the importance of the reverse path forwarding check. The outbound interface of a multicast routing entry is usually determined by the multicast routing protocol. The multicast routing protocols will be covered in another course, one course away from this, one chapter away from this, called PIM implementation and configuration. A multicast routing entry contains a multicast source, a multicast group, and therefore it is called a source group entry. But how exactly does this router implement a reverse path forwarding check? Let us talk about that for a moment. What is involved in the reverse path forwarding check? Well, multicast data packet reaches a device like a router. The router reads the source IP address of the multicast packet, which is now the multicast source IP address. It then searches for the outbound interface of the Unicast route in its IGP to reach the multicast source in its local routing table. When it finds this outbound interface, it means it is the interface closest to the multicast source. Now the question is the outbound interface, which is the interface closest to the multicast source, is it the same as the inbound interface of the multicast packet I've just received? If it is not the same, then the reverse path forwarding check failed and the packet will be discarded. But if it is the same, then the multicast packet was received from the correct interface and the multicast packet will be received and then processed accordingly. This is exactly what happens here. When we run the reverse path forwarding check route, it finds that to reach source 1, we need to go through interface 1, not interface 2. So interface 2, if another traffic comes from this source through interface 2, it will be blocked because it does not pass the reverse path forwarding check. But how do routers select routes when doing the reverse path forwarding check? Because as you can imagine, each multicast router will search its routing tables. Of course, as I said, they get this from the routing tables. Now, we mean the Unicast routing table and the multicast BGP routing table or the multicast static routing table. It's going to be one of those three. The Unicast routing table for the IGP, and then the multicast BGP routing table, or even the multicast static routing table for the route to the packet source. How does the reverse path forwarding check route select the best path? The routes can be selected among 1 Unicast routes, 2 multicast BGP routes, and 3 multicast static routes. If a router has all these routes, it performs a reverse path forwarding check on the multicast packet in the following way. So this is the source IP. It will be checked in the Unicast routing table and also in the multicast BGP table and also in the multicast static routing table. Now from the routing table, we select the candidate reverse path forwarding route, including its outbound interface. We shall do this for all the different routing tables. And then we start selecting out of all the routes we have just got. We select based on the longest match, like normal route selection. Now, if we have the same length of the subnet mask, then we are going to use the preference value, like just other routing protocols. But if the preference value is the same, we are not going to the cost next. We are going to prefer the multicast static route to the multicast BGP route to the unicast route. This is the preference order. If they are all there, then we shall use this one. If there is only these two, then we shall use multicast BGP. If there is only unicast, then of course it's the one we shall use. That is what we shall use to select the reverse path forwarding route, which includes the outbound interface, in order for us to determine the reverse path forwarding interface that will determine the interface closest to the multicast source. That is what happens for the multicast router to select to determine whether the inbound interface is the rightful interface for the traffic. We also talked about the multicast distribution tree, which we said is really the path forwarding, the forwarding path of multicast traffic. Now, it is required that no loops and no suboptimal paths or even duplicate packets occur during multicast data forwarding. Through the reverse path forwarding mechanism and multicast routing protocols, a loop-free multicast forwarding path, also called the multicast distribution tree, without suboptimal paths or duplicate packets can be established on the multicast network. Each multicast distribution tree takes the multicast source as the root and group members as the leaves. So this is going to be the root, this is where everything begins from, and these are the leaves, this is where everything is headed. The multicast data is then going to be forwarded based on this tree. In this example, this tree says the root will send to this fast hop router, and from the fast hop router we can send there if we want to send to this subscriber. If we need to send to this subscriber another leaf, then we shall send there. So as you can see, replication will happen here. For the same bucket, we'll have a copy that side and a copy that side. Here it will be forwarded there, and here it will be forwarded there. What is the data forwarding process? It's exactly what I've talked about. Each of these routers has a multicast routing table and the reverse path forwarding route. In this case, the multicast source will send a packet with destination IP, the IP address of the group, and the source IP, the IP address of the multicast source, which could be a media server. The multicast routing table will have the source and the group. It will have the inbound interface and the outbound interface. This is the multicast routing table for router 1 here. So based on the multicast routing table, of course, after performing the reverse path forwarding check, router 1 will forward the traffic to router 2. Router 2 has its own multicast routing table and has its own reverse path forwarding table. It will check the reverse path forwarding table to confirm that the inbound interface is indeed the best interface that passes the reverse path forwarding check, and then will send out the traffic out of the outbound interface in respect to the PIM routing protocol. This will be sent to router 4 that also has its own multicast routing table. The inbound interface, after performing a reverse path forwarding check, the outbound interface, which is going in this case to be determined by IGMP, which is going to be an IGMP interface that forwards traffic, knows which groups are joined by which members, and then the source and group, as we have already mentioned. The details of what happens within this multicast domain or the multicast forwarding network are discussed in protocol-independent multicasts implementation and configuration. It's another chapter. So Let us introduce the multicast protocols now. We have seen that a multicast network needs to establish forwarding paths based on multiple multicast protocols. Actually, I did mention that IGMP will run on the receiver end, and it's going to be used to inform the multicast network of the locations of different group members and the multicast groups that those members are joining. The protocols that work on the multicast forwarding network include protocol-independent routing and also include MSDP and also include MBGP. PIM is mainly used to generate the multicast distribution trees inside an autonomous system. MSDP is mainly used to help generate inter-autonomous system multicast distribution trees, and MBGP is used to help perform reverse forwarding, reverse path forwarding, reverse forwarding. What is this supposed to be? Excuse me. A reverse path forwarding check on inter-autonomous system multicast traffic. So these are the three protocols we are going to use. We are going to use PIM, which is protocol independent multicasts. We are going to use MBGP, which is multicast border gateway protocol, and we are going to use MSDP, which is multicast source discovery protocol. Oh, excuse me. Here, we are going to use PIM, Protocol Independent Routing, Multicast Source Discovery Protocol, and Multicast Border Gateway Protocol. The Border Gateway Protocol is used to perform a reverse path forwarding check on inter-autonomous system multicast traffic. The Source Protocol is used to help generate an inter-autonomous system multicast distribution tree, and PIM is used to generate the multicast distribution tree inside an autonomous system. Those are the protocols that are going to be run in the forwarding network of multicasts. And this brings us to the end of this chapter. Thanks for watching this video. I hope it has been informative for you. Let us meet in the next chapter, which is going to be IGMP implementation and configuration. But before we leave, there is a quick quiz to test your understanding of what we have just covered. The first one requires a single answer. What is the range of IPv4 multicast addresses? The second one requires more than one answer. Which of the following statements about the functions of the reverse path forwarding are true? So you choose A and B, or B and C, or A and C, or ABC, depending on what you've seen in this section. And you choose one of these ranges that is for IPv4 multicasts. All right, let us summarize. Multicast is mainly used to solve a number of problems when using point-to-multipoint traffic forwarding and carrying it in either unicast or broadcast mode. The problems in unicast mode are that when increasing the point-to-multipoint service terminals, the bandwidth consumption or the pressure on the source server may be too high. And if we are using broadcast mode, there are going to be a number of problems accompanying point-to-multipoint traffic transmission that do not occur, but the broadcast mode is going to have a security issue, as users who don't subscribe to the source are going to be receiving the traffic, which is low security. A multicast network consists of three parts: the source end network, the multicast forwarding network, and the receiver end network. We have also mentioned that the receiver end network will use protocols such as IGMP. The multicast forwarding network will use protocols such as PIM, will use protocols such as MSDP, will use protocols such as MBGP. The multicast forwarding network is responsible for forwarding multicast data between multicast routers, but problems such as loops, suboptimal paths, and duplicate packets may occur. These problems can be partially or completely solved using the reverse path forwarding check. Thank you.